So let me just give you another example of a Lie algebra. So in classical mechanics, we have, and I apologize to the ones who are the math students who haven't seen classical mechanics. We have a physical system which has certain coordinates, qi. These are known as generalized coordinates. And they have certain conjugate momentum defined. These are called canonically conjugate momentum. And they satisfy what is known as a Poisson bracket. So the Poisson bracket between the Q's and the P's, I think, is this, right? So what is a Poisson bracket? In general, suppose you have a function. That's okay. Just can I take this call? Sorry. Hello? হ্যাঁ বলেন। হ্যাঁ কেন আমার একটু কাজে আছি, মিটিং এ আছি। উনাকে বলেন যে আমি মিটিং এ আছি, উনাকে উপরে 6 তলায় গিয়ে বসতে বলেন, আমার 7টার সময় মিটিং শেষ হবে। কে আপনি ফোনটা দেন তো। হ্যালো, কে বলছেন? Hello, sorry about that. This is the grand Bangladeshi tradition of going to a person's house without any warning whatsoever. All right, so suppose that we have a function of these variable, let's call it f, so fqp, and another function g, which is also a function of f, q, and p. Then we can define a Poisson bracket. I think it's between these variables f and g, and it's defined to be, I think it's derivative with respect to qi first, and derivative respect to pi. So here we have a repeated index, so there's a sum, and then derivative with respect to qi of g, and the derivative with respect to pi. Okay, so this is the Poisson bracket. And of course, if I take f to be, say, q, and g to be, say, p, then qi pk is going to be derivative of qi respect to, say, qj, derivative of pk with respect to p of j, and then minus derivative with respect to, say, pk with qj, derivative of qi with respect to pj. So the second term, because q and p's are independent variable, we are assuming them to be independent variable, and we are doing in classical mechanics, the second term is going to be 0. And so the first term is going to give me, the first guy is going to give me delta ij, the delta function, the Kronecker delta, and the second term is going to give me kj. And there's a sum over j. In using that fact, we have delta ik. So we see that qi pk is equal to delta ik. Okay? So now this Poisson bracket, from its definition, it's actually antisymmetric, right? If I replace G, if I replace F with G, and if I replace, say, G, F with G, and G with F, right? Then I have over here, I'll have G, and there'll be F. And then we see, and this will be F, and then we'll see G. So we see that over here we have del G, del Qi, which is this factor. And here I will have del F, del Pi, which is this factor. So replacing, exchanging these two things, it gives me minus of something, of the whatever it was. So F of G is minus GF. So it's a skew symmetric product. And then you can also verify that if you take two functions, f, g, and say h of p and q, and you compute this thing plus cyclic combination, then that gives you 0. So the Poisson bracket is also, it's also a Lie algebra. Okay, so there's a Lie algebra underlining the geometry or the symmetry of phase space. Okay, any questions?
So would you please write the Poisson bracket using prime sign, like DDT differentiation as a prime sign, so it can be visualized clearly?
What do you mean prime sign?
I mean, f prime is like DDT.
Because right. So we can't do that because the Poisson brackets we are not taking derivatives with respect to time. We are taking derivative with respect to the spatial, with the generalized coordinate and their conjugate momenta. Now the conjugate momenta are defined in the following way. If Q I is a generalized coordinate, then P of I is defined to be the derivative of the Lagrangian with respect to Qi dot. Okay, that's the definition of Pi. And from the Lagrangian, we go to the Hamiltonian by, I think there's a minus sign missing, or I don't really care about that. It's as we replace Qi dot with Pi. Because the Lagrangian is a function of the generalized coordinates and the generalized velocities, but this is what is known as a Legendre transformation, and I covered this in great detail in my statistical mechanics course. And but from there you get to the Hamiltonian, and the Hamiltonian is a function of the generalized coordinates and the generalized momenta, or the canonically conjugate generalized momenta. So there is no derivative when it comes to the Poisson bracket, which is defined here. There is no derivative with respect to time.
Okay, sir, got it. I didn't take classical mechanics, so was not sure.
Yeah, I also defined this in StatMech. I don't know if you were in that course. There was actually even a tutorial on the Legendre transformation. Or yeah, I think so. I also, I mean, I've done it many times, sometimes in quantum mechanics, sometimes in statistical mechanics. I always go back and do this. But yeah, you can look it up, and then if you have questions, I can also answer those, individually offline.
Yes, sir.
Okay, so is this clear why the Poisson bracket is also a Lie algebra?
Yes, sir.